Hi, my name is Tabitha Stein. I'm the Vice President of Market Development here at the American Institute of Steel Construction. We thank you for joining us today to talk about our online forum that we're sponsoring with Skidmore, Owings & Merrill and our speaker Benton Johnson to talk about our research project that we recently completed focusing on timber research with structural steel framing. Our speaker today, Benton Johnson, is a PESE lead green associate who joined SOM about a decade ago after completing his master's degree at the University of Minnesota. He has worked on a broad range of domestic and international projects during his decade there, including super tall buildings, mixed-use developments, convention centers, hospitals, and even single-family homes. His work has also included innovative research projects such as AMIE 1.0, a 3D printed demonstration building created with the Oak Ridge National Laboratory. He also worked with the Timber Tower Research Project and has been working with testing at Oregon State University and most recently with us on our Timber and Steel program for residential buildings. Today, Ben is going to talk about that research project along with future insights looking at residential construction, why it provides such a vital, important part to the construction market today, and how structural steel can team up with timber to find a viable solution. With that, I'm going to hand it over to Ben for the conversation today.
Okay, thanks for having me today. Today we're going to be discussing our developed steel plus timber system for residential buildings, specifically mid-rise and high-rise buildings. We'll be taking a look at this effort that has been a joint research project between the AISC and Skidmore, Owings & Merrill. The outline of today's talk is going to cover three main sections. The first one will look at steel systems that have been developed to date for residential construction. We'll then discuss composite cross-laminated timber floor systems that use reinforced concrete topping slabs as the basis for the research project going forward. And then lastly, we'll talk specifically about the structural steel frame and timber decking system that we've developed for mid and high-rise buildings. To start, we want to put things into context and why this is important to develop sustainable systems for mid and high-rise buildings. When you look at apartments and condominiums, hotels, student housing, and senior housing, they account for 27% of the total construction volume based on AISC's national market analysis. This is a very large percentage of construction. And so what we want to be able to do is develop appropriate structural systems for these buildings to give more differentiation in the marketplace and more options for our clients. Residential buildings have a unique set of criteria that need to be considered. For starters, there's a unique layout of room and services that change depending on the unit types and positions. And these can be relatively different from level to level, whether it's a studio 1, 2, or 3 bedroom unit, and they can change from story to story. And so when you compare it to an office building, accommodating these sometimes random seeming room layouts is a major criterion. One of the ways that this is achieved is with a flat soffit condition. And what we mean by that is having a flat bottom of structure and no projecting beams. This allows you to plan out units of any size and configuration without regard to the structural system. The only thing you have to contend with are the columns in the space. Residential buildings also need to consider the high acoustic requirements associated with this construction type. The building codes demand a certain sound transmission coefficient, or STC, that grades the amount of acoustic resistance between units. It's obviously very important for a residential building because when you're trying to get some sleep while there's a large house party happening above you, you don't want that noise coming down into your space. And then lastly, the floor heights and costs. One of the things that drives the cost on these buildings are the floor-to-floor heights. And so if we can minimize the structural depth associated with the system, we can reduce floor-to-floor heights and then the associated cost. All of the research we're going to show you today is predicated around an SOM design benchmark shown on the right-hand side. This uses a conventional cast-in-place concrete frame with 8-inch thick post-tension slabs. We would consider this to be the standard of what you would see in residential construction typically today. It's a very, very economical system and allows for all the things that are just discussed. So when we go and talk about our proposed system today, it's going to be through the lens of this benchmark concrete building. So let's talk about some of the steel systems that have been designed for residential buildings today. One of the good systems out there that we've seen is the girder slab system. It's a composite structural steel beam that's asymmetrical and precast concrete floor system, typically hollow core plank. And this system uses a structural steel frame where the asymmetrical beam has a larger bottom flange that allows the hollow core plank to be set on the bottom flange and then grouted in for its final condition. It uses a castellated beam style structural frame that allows the concrete to flow through and to join them together. And here you can see some of the erection of a frame using this system. So the structural steel goes in, and then the hollow core planks just sit on the bottom flanges. And this creates an almost near flat soffit condition. So then again, you only have to contend with the position of the columns related to the unit layouts in the building. And this is the final product. As you can see, it has a lot of the same benefits that you would see with other technologies in terms of unit layout and space planning. You can get large bays with minimal obstruction, so a very good system. There's other approaches as well, like the Pico group shown here. It's a similar concept where you're using a special structural steel beam with then some hollow core planks resting on it. This beam uses a trapezoidal shape where the bottom flange again is extended to accept the precast, but now when the concrete is poured and grouted in, it makes a continuous beam. And here you can see that operation right now where the concrete is getting poured for the final condition. And this is a built example here. Again, a similar approach here where you have a flat soffit condition using the post-tensioned or the pre-tensioned hollow core planks. And lastly, we wanted to show a different approach. The first two were showing the hollow core planks. This one uses actually a deeper deck system. This is the VersaFloor system using a deep deck profile, which can give you, I believe, 7-inch deep metal decks. And there's a couple different ways that they can use these. You can do it with conventional structural steel beams or drop down. And they've also developed a system called the VersaCore, which uses a bent steel plate as the final beam. And in this way, basically, all of the steel is acting like leave-in-place formwork. So again, another operation that's got some similarities here, but again, a near flat soffit condition for each of these types for the discussions that were mentioned earlier. And here you can see them pouring the floor. So again, the end product for each of these is essentially the same. You have a concrete slab as your substrate for finishes and for everything else in your building, a structural steel frame, but very few beam conditions to deal with. So moving on and looking at new opportunities, let's talk about composite cross-laminated timber and concrete floor systems. SOM has been researching timber construction for over 5 years now, looking at mid and high-rise buildings. We've shown 2 reports that are available on the left-hand side, with 2 more that are going to be published in the coming days, that being the AISC report that we're discussing today, but then the Oregon State report shown some of the testing images on the right-hand side. The research that we did looking into the high-rise building started with a survey of all the available timber technologies that we had available to us. And this ranges from the timber elements themselves, shown on the left-hand side, to the connector types, shown in the middle, with some of these fancy screws and glued-in plates. And then lastly, looking at timber concrete composites, an idea of combining the 2 materials as shown on the right-hand side. If we look at the timber elements themselves, there's a lot of different available technologies out there. And we put them all into a category of mass timber. And what we mean by that, when we say mass timber, is things that have similar properties to a natural heavy timber element, but that are built up from individual pieces of wood. And so in that family would involve things like glue laminated timber columns and beams, like are shown on the upper left-hand photo, nail laminated timber decks, which is shown in the lower left-hand corner, and then also the finished product on the upper left. And the nail laminated timber decks are essentially 2x6s or 2x8s that are nailed to each other on the side face along the entire way to build up a solid timber deck. And then lastly, there's cross-laminated timber on the right-hand side, which is essentially like mega plywood, where you have boards that are glued on their face and then alternate in directions each 90 degrees. We'll focus primarily on cross-laminated timber because we see that as the way of the future over some of these other technologies. CLT itself has a lot of advantages. It's prefabricated, lightweight, the thermal insulator, and it has certain marketing advantages. But there's other issues too that make it attractive for residential construction, including its two-way spanning capabilities. Because of the cross-lamination and orientations changing every layer, it allows the material to span in two directions. And that's really important when you start to look at floor penetrations and floor penetrations that don't necessarily align with your structural module. It's nice to have that aspect because it allows you to get loads around the areas. One of the challenges with cross-laminated timber is the acoustics associated with it. Wood is about 1/5 the density of concrete, and so it becomes very lightweight even when it's a solid timber floor system. And so to solve the acoustics, there's a couple of ways to do it. One is to have a drop ceiling as shown on the left-hand side. That's got a lot of challenges associated with cost, and it also increases the ceiling section. On the right-hand side is a more common approach, and that uses a concrete topping slab, be it non-structural or structural, to add a little bit of mass into the system and to isolate the layers from each other. And in doing so, you can get an STC that's code acceptable and still expose the bottom side of the CLT, which we see as a good approach. The other thing that you need to be aware of when talking about cross-laminated timber is the fire resistance. Again, we use the term mass timber because it has a lot of similarities with heavy timber, including the charring response to fire. And so when we look at the fire design of CLT, we have to consider three things: the structural resistance, and that its ability to carry load long-term after it's lost section due to charring; an integrity failure, which prevents the movement of heat and flame through to another side; and then lastly, the insulation failure. Well, we mentioned that CLT is a natural insulator, and so there's very little issue with the temperature increase on the other side. It's really the structural resistance and integrity that we need to consider. Considering those two failure modes, there's two different ways to look at it. And the first is with the charring behavior shown on the left. Charring is a natural phenomenon that insulates the structural core of the timber element, keeping it cool and structurally sound, meaning it can carry load. And so there's a lot of methods out there that have been substantiated by testing results that allow you to calculate a reduced strength due to charring in a fire condition to verify structural integrity. And that's how you solve the first one. The second one is with testing, and that's where we're trying to look at the actual integrity failure and not allowing flame to pass to the next level. And this is actually the more concerning thing when it comes to timber. There's a lot of reserve capacity, but letting the flames pass through is actually a bigger issue. And so when these tests are done, you can see on the right-hand side, they're typically showing failures in integrity. We can solve that, again, with a concrete topping slab that you might need for acoustics. And so this is where it leads us to in terms of composite concrete topping slabs and what we want to achieve. We know that we want the concrete topping slab to solve our acoustic issues so that we can expose the underside of the timber. The concrete topping slab also increases the fire resistance by creating a non-combustible barrier in between levels that cuts off the chance of an integrity failure. By making them structural concrete topping slabs and composite, we can actually increase the span length. So that means fewer columns on the inside and easier to plan out room layouts. When made structural, the seismic diaphragm can also be handled just in the reinforced concrete portion itself, so it simplifies the design. And lastly, it gives it a measure of durability by protecting the top surface of the CLT. So when you look at a typical build-up, what you often see is the 5-ply cross-laminated timber, which is approximately 6 3/4 inches thick, plus a concrete topping slab. Our testing at Oregon State University is using a 2 1/4 inch concrete topping slab for a total thickness of 9 inches. And that's pretty compatible with what you would see in concrete construction for a residential building. Usually it's about an 8-inch concrete slab, maybe a little bit thicker, it can need longer spans. So it's compatible in terms of floor-to-floor heights and ceiling sandwiches. But we don't give up the mass benefit of timber. Looking at that composite section, it's equivalent to 44 pounds per square foot of mass. If you compare that to what's considered to be one of the lighter floor systems, a 2-inch deep metal deck plus a 3 1/4-inch lightweight concrete topping slab, that equates to about 42 pounds per square foot. So looking at that 9 inches of construction, you would expect it to be pretty heavy, but it's not. It's actually equivalent to a pretty thin, lightweight concrete slab. The topping slabs that we use are typically normal weight concrete, and that comes down to really about availability. Lightweight concrete isn't available everywhere, so we try to use normal weight concrete where possible. It has a couple other benefits for us when using normal weight concrete. Normal weight concrete has an increased tensile capacity compared to lightweight concrete, so you would typically expect less cracking in your slabs long term. And then also the additional mass gives you a little bit better acoustic performance, which is important for the CLT. Now, lastly, it comes at a cost of the increased mass from a structural perspective, whether it be foundation design, seismic design, column design. It adds up. So if you compare the same design using lightweight concrete versus normal weight concrete, there's not that really much of a difference. It's 38 PSF versus 44 PSF. So when you compare the two types of materials, really it just comes down to availability. All those other things are basically details. It changes the mass a little bit, changes the performance a little bit, but normal weight concrete's available everywhere, so that's what we like to proceed with, and that's what we tested at Oregon State. Here's the Oregon State testing program. You can see their laboratory here with 3 test specimens down low. We studied over 20 different tests and 14 different specimens, all full scale, looking at different ways to connect and make composite action. One of the connectors that we use most frequently is these inclined screws, and you'll see those in the reports that will be published soon and how we connect them. One of the types of tests that we did was a simple span, positive bending test, looking at the effect of different connector types. So we looked at glued-in connectors, we looked at mechanical connectors, we looked at some standard shear stud connectors with screws. Also, we could understand the different performance and the available strength and stiffness that we have from them. We also did a full-scale mock-up looking at a 24-foot span in between supports, shown in this photograph here. This test shown right here is at 8 times the design load that you would typically see. So the weight of that it's simulating from the load of the actuator is equivalent to about 600 pounds per square foot applied on that floor system, and that's what's making it deflect so much. And so looking at these composites, by making them continuous, we can get longer spans, which are better for residential layouts, all while not adding additional materials. We're just taking the materials we already need, meaning CLT and concrete for acoustics, and making them composite. So moving on now to the main portion of the webinar here, which is the structural steel and timber system that we've developed with the AISC. Looking at cross-laminated timber and composites, it really is a new technology, and that creates a new opportunity for the structural steel industry. If you look at the different types of floor systems that have been available, we started with things like clay tile arches and other floor systems which have now been defunct and replaced by metal deck slabs and precast concrete slabs and everything else. And so the idea of a structural steel frame has been a consistent theme in the construction industry for over 100 years. But the actual floor systems that we use and plug into them has changed and will continue to change over time. So now that we see this new decking type system of these composite cross-laminated timber floors, it really is a new opportunity for structural steel frames to take a look at and to see what kind of benefits can be had by combining the two. So let me show you a little bit of the construction sequence and how we think a system of this nature would work. You would start again with a structural steel frame of beams and columns, and that would be erected for 1, 2, 3 stories ahead of the rest of the operations on site. After the steel frame is erected, you would then drop in your mass timber decks. In this example, we're talking about cross-laminated timber decks but you could also do nail laminated timber if it suited your project. After the mass timber decks are dropped in and installed, sitting on the bottom flange of the steel beam, we place reinforcing in the top slab. This would be welded wire fabric typically, and then if you need additional capacity over the beams where you have negative bending or diaphragm loads near a core, you could add additional rebar. And then the topping slab is poured. Taking a closer look, we start with a structural steel beam. Again, we're suggesting an asymmetric steel beam to facilitate the placement of the timber decks. You drop in the timber decks to have flat soffit condition. Install your rebar and composite connectors, and then pour your concrete to make the entire system good. And that's your final product right here. And so what's kind of interesting about this one is that because it's an easy product to CNC, the cross-laminated timber, it's easy to CNC the end connections there so that we can actually get a truly flat soffit condition by routering out the thickness of the flanges of the steel beams that it supports. Looking at the details of the research project, which is going to be published on SOM.com in the coming days, it really breaks down into a few different sections, but the goal is to show how the system would be applied to the SOM design benchmark building, but more importantly, show the details in the concepts that would be used, which could be applied to framing bay sizes of any size for a real project. It goes through a few different zones, a few different sections, tries to explain why we're trying to do these things. What are the critical issues in the design process that led us to these decisions? And then we show the approach, and then we finish off with non-structural considerations, and then a comparison to the benchmark. Talking about the benchmark, this shows you the architectural floor plans on a typical floor. The yellow sections are common corridor areas and core areas for the elevator core on the right and the remote stair on the left. The green and orange just show differentiations between units and their demising locations. As you can see here, this floor plate accommodates a wide range of unit sizes and shapes, and is pretty consistent with what you see in a lot of buildings of this height, sort of 10 to 12 story range. This is the structural layout for that same building. You can see there's a reinforced concrete core around the elevators and stairs to the right, and then a reinforced concrete core around the stair to the left, with some additional isolated concrete walls connected into that stair core to give it a balanced stiffness with the core to the right. There are only 3 concrete columns between the cross section of the floor plate, and we do that to reduce the number, also with a small, well, actually a moderate slab cantilever on the 2 sides. It's an 8-inch thick post-tension slab, which is able to achieve these spans and also solves the acoustic issues as well. Here's our proposed framing solution using our steel and timber system. Now, the composite cross-laminated timber decks cannot span as far as a post-tension concrete slab. So we have to reduce the spans in order to get the building to work with the same thickness as shown earlier. And so we did this by adding in another line of columns. So instead of 3, we have 4 columns, which we see as a reasonable thing to do and doesn't really impact the ground layouts too much. The elements highlighted in red are structural steel. Everything else would be composite cross-laminated timber floors. We provided 4 asymmetric steel beams running along the axis of the floor plate, with the timber decks spanning in between them. We located those framing lines so that they would not hit any of the potential floor openings in the system. And then you can see all of the floor openings that go directly through the composite cross-laminated timber deck. The 2 core areas highlighted in red are structural steel framed cores with composite metal deck slabs. We didn't want to provide any combustible construction within the core area because, again, this is intended for mid and high-rise buildings where performance fire design may be required. And so keeping the egress areas non-combustible feels like a reasonable thing to do to enhance the fire performance. This is the typical detail looking at an interior beam. So what you have is you have the asymmetric beam, steel beam, that's formed with a WT section and a thickened bar welded to the top. That asymmetric beam section allows the cross-laminated timber floor planks to be dropped straight down and supported on the bottom flange. The cross-laminated timber decks are notched as shown to create a completely flat soffit condition. And they're also notched to facilitate the concrete placement of the topping slab. This detail also shows the composite connectors to the topping slab and reinforcing over the supports. That reinforcing is continuous and allows the cross-laminated timber floor planks to span as far as we indicate on the framing plan. This is a typical detail at the exterior condition. At the exterior condition, we stop the steel beam about 1.5 feet away from the edge of slab, and we did this for the particular constraints of the benchmark building. It's not necessarily a requirement for the system, but we showed it anyways to see how you could achieve a longer slab cantilever with a bent plate basically bolted to the bottom flange of the WT shape. This has some other benefits later on that we'll discuss when we're talking about the exterior wall connection. But again, a very similar detail that allows for a nearly flat soffit condition. If we zoom in and take a closer look at the framing bay, you can see the typical approach. The typical approach is to have 2 columns that are spaced at some reasonable module. We would expect anywhere in the range of 20 to 28 feet. We're showing 27.6 at this location. Now the challenge with going 27.6 is that the steel beam tends to deflect a lot. And so we want to reduce that so that we don't have to have any secondary floor leveling mechanisms. And so we're kind of stuck here because we need to fit the steel beam within the thickness of the floor sandwich, and we also need to make that span. And so in order to do this, what we did is provided moment connections at the ends of the steel beams. And we did that with end plate moment connections, which are a very economical way to do it if you're just trying to get deflection reduction. These are the typical steel details that we proposed at the ends. At the ends of the WT sections, you would have a thickened end plate. Now, this is a conventional connection type that's shown in other design guides from the AISC. That end plate would be bolted to the face of the column with 4 high-strength steel bolts. The actual design of the connection would be governed by strength. The beam itself would be governed by deflections, typically. Now, one thing that we need to consider when we're doing these end plate connections is fit up in the tolerance in the field. We've indicated end plate shims between the column and the end connection in this configuration to take up that field adjustability. Other ways can also be done, including prefabricated column trees with drop-in sections as well. There's a lot of different ways to approach this. This is just one, but at the end of the day, we think that rigid end connections for continuous beam bending is going to be necessary to control deflections. Taking a look at the seismic resistance of the building, we've indicated eccentric brace frames. Now, what's important is that we need to consider the seismic resistance associated with the system for an overall comparison to the benchmark building. The benchmark building is located in California, so high seismic region. The seismic resistance of the building is not outside the scope of the study, but we didn't want to focus too much on the exact seismic resisting system. We've shown EBS, but these could easily be buckling restrained braces. They could also be moment frames around the perimeter. It could be a reinforced concrete core, if you like. There's really no effect on our proposal because our system is geared towards the gravity framing areas of the system, and you can plug and play whatever seismic resisting system you need. Where the seismic resistance comes into a little bit more play here is actually in the diaphragm design. So the diaphragm design in this approach was relying only on the reinforced concrete topping slab to deliver the seismic loads to the core. And we think that that's reasonable to do with additional reinforcing placed where necessary for collector elements and then also for transfer into the lateral load resisting system. One of the benefits of the composite timber frame compared to, say, a reinforced concrete building is that the seismic loads are about 30 to 40% less. And so when we're looking at the diaphragm loads themselves, particularly when we use a highly ductile system like buckling restrained braces, is actually quite low. And so when you combine a ductile seismic resisting system with a low seismic mass gravity framing system as we're proposing, we're able to achieve the diaphragm resistance as shown. If you have a heavier system or a lower R factor, you might need to actually rely on structural steel beams as collectors and not just the reinforcing, but that's going to be a project by project decision. This is looking at a couple of different details that we have included in the drawing set that will accompany the report, which will be published online. It shows two different things. On the left-hand side is a typical edge-to-edge connection of a CLT member. Again, we're using inclined screws here just to have vertical compatibility between the two planks. We're not trying to get any seismic load resistance out of them. What we are showing is additional reinforcing where required to carry those seismic loads across that joint. Similarly, on the right-hand side, you can see this transition between the composite cross-laminated timber system out in the typical floor plate and the metal deck system inside of the cores where we want non-combustible construction. And here we've actually identified additional diaphragm slab reinforcing as required at the core. Again, we think that's appropriate for a building of this size and scale. Taking a look now at a more detailed discussion of fire resistance. As discussed, there's two things that we need to be mindful of: the structural resistance, the load carrying capacity, and the integrity, the ability to prevent heat and fire and smoke to pass between levels. We're solving the integrity issues with the cast-in-place concrete topping slab, which is allowed to flow down and encase the entire steel beam. The structural resistance of this system is a different challenge. It's our expectation that the composite cross-laminated timber floors would satisfy any required fire resistance through the charring behavior. And that would allow us to expose the cross-laminated timber soffit, which would reduce costs by letting it be exposed, and then also gives a unique appearance to the space, which is kind of interesting. The steel beam, the asymmetric steel beam, we would also expect to be unprotected in a fire. And we think that has a possibility because of the unique conditions of the mixed materials. The cross-laminated timber is a good insulator, and it's going to keep the topping slab and the concrete encasement around the steel beam relatively cool in a fire. And what that does is it actually provides a perfect heat sink for the steel beam to reduce its temperature loads by putting its temperature heat into the topping slab and the encasement. And so by doing this, it will keep the temperature of the steel beam low enough that it should be able to support loads unprotected. That is our anticipated approach, but would need testing to confirm. But that's where we think this is going to go. The columns would still need to be fire protected if a wide flange as shown. Again, the focus of the report was the typical gravity framing systems, but in order to make an appropriate comparison to the benchmark, we have to take a look at the foundation design. The foundation design for the benchmark building used isolated spread footings and then a combined mat foundation under the cores. The total foundation loads when looking at the gravity and seismic overturning effects are substantially lower for the proposed steel and composite timber system. As a result, the foundation demands go down substantially, and there's significant savings in the foundation levels. Taking a look at other non-structural considerations, the first one we want to take a look at is the typical exterior wall detail. This shows a curtain wall system being supported off of the reinforced concrete slab edge discussed earlier. Again, this is one of the reasons why we like the composite approach, is that we can extend the reinforced concrete section out to support the exterior wall without having to retool or change the type of connectors. So if you're using like a Halfin insert or some other proprietary connector for these things that are designed to go into concrete, we don't need to change any of that for this system. We can go ahead and provide that same approach here with very little concern. Now, another thing to keep in mind is that we're gearing this system towards mid and high-rise buildings where a higher level of fire performance would be required. And if you look at the performance of the exterior wall system in a fire, we need to concern ourselves with that interface between the edge of slab and exterior wall condition, where we would actually have the smoke and fire stopping systems at the edge. And by providing non-combustible construction for that attachment, it increases our reliability of our connection and increases our robustness of that connection in a fire condition. So all good things for the system to help it satisfy performance-based requirements. Lastly, this shows the system's comparison between the steel and the concrete benchmark system. We've provided structural steel quantities, slab reinforcing quantities, concrete quantities, and cross-laminated timber for the system, alongside a takeoff material quantities for the benchmark building. And when you compare the two, they use a similar amount of volumetric materials, meaning concrete plus cross-laminated timber. And if you look at the reinforcing in the benchmark system versus the structural steel and reinforcing in the proposed system, they're not all that off, considering that post-tensioning is much more intensive than reinforcing from a cost perspective. So initial cost analysis of these two systems shows that the proposed system could be competitive depending on the project requirements, but it does take a full building evaluation, considering all the things like the foundation impacts, considering things like non-structural implications and attachments to the frame, as well as speed of construction, which is perhaps the most important thing. These prefabricated systems will be able to be constructed much quicker than cast-in-place concrete, particularly when we're talking about high seismic zones that might have congested rebar within the core walls. So that information is available from the AISC. Looking back at our proposed systems and now talking about the conclusions from today's webinar. The system was designed really around economy of labor and material. What we wanted to do was start with a composite cross-laminated timber deck thickness that's suitable for acoustics and fire resistance. 5 or 6 plies with a 2 or so inch concrete topping slab is about the thickest system buildup you want to look at. So if we start from that and say how far can we span with it and set out our framing lines, we end up getting to the system that we showed here today. But it's also about economy of labor. And that's why we showed the asymmetric steel beam, because you can drop the timber planks so much faster onto the steel frame and build it much faster. That's really important because the speed of construction and the savings is one of the key benefits of these types of structural steel framing systems for residential buildings. They're prefabricated, they're much faster to build. We talked a lot about the lightweight savings associated with the system. The structural frame is less than half the weight of a concrete frame. And when you add in the non-structural components, it's usually about 60 to 65% of the weight. You can get a lot of benefits for certain sites with a weight savings like that. So for example, if you have a site that might be looking at the difference between deep foundations and shallow foundations, that might be a good reason to consider a system like this because of those savings that you could see. And they're specifically important for seismic resistant system. The system is robust and durable. We've shown how it can accommodate floor penetrations from multiple unit type layouts, and it's got durability enhancements with the concrete topping slab that are going to extend its design life far beyond what's required by code. And then lastly, it's got room to improve. Cross-laminated timber really is a new technology, at least in North Americans. And right now, part of the challenge is looking at manufacturers and stock, and it's rapidly evolving. And so we think it's really important to keep our eye on the technology and make sure that we're using it to its biggest advantage but not forgetting how it can be combined with other systems like structural steel that can really play to the strengths of both materials and open up new market opportunities for structural steel. New technology, new opportunity. We see a lot of benefit here, and that's why we've engaged with the AISC to deliver this study. Everything that I've shown today is going to be released on slm.com under research. That's going to include the 40-page report that shows the different things, as well as 7 or 8 pages of sketches which identify the actual framing layouts. That report is also going to be released alongside our testing report at Oregon State University. So for those of you who are not familiar with composite cross-laminated timber floor designs, you'll also have that research report available to you so that you can get a little bit more background information because we show a lot of the results of that OSU testing and lessons learned in this report for the AISC. So with that, thank you for your attention.
I want to thank Ben for joining us today. It's been a great opportunity to have him here to share his insight and his expertise on the topic. If you have any great ideas, solutions, or recommendations for future research on how we tackle residential construction or any innovations with structural steel, please reach out to us today by contacting the AISC Steel Solutions Center at solutions@aisc.org. We are your one-stop shop for all ideas and innovations related to structural steel. So thank you again for joining us, and please reach out if you need anything in the future.